So far in this series, we've taken a look at Newton's laws of motion and did a bit of an exploration on the difference between gravitational and inertial mass. I want to follow up on that last bit just a bit more to talk a bit more about the distinction between gravity and weight. So let's just start by thinking about a rock that is falling down. If I draw and we will for the moment assume that there is no air resistance, but we'll deal with that later. So we can go ahead, draw a force identification diagram. There are no contact forces. So our only long-range force is gravity. And we can draw a free body diagram for this object. That's it. Okay. So in our model of gravity that we have at the moment, we say that the force of gravity on something is equal to its mass times g. So object's mass. And this lowercase g is called the local gravitational field strength. And what this does is it summarizes a planet's influence on objects. This depends on many things. It depends on the mass of the planet. It depends on how far away you are from the center of the planet and so forth. But if you are within 11 kilometers of the Earth's surface, turns out that G is equal to 9.8 newtons per kilogram to within 1%. There are some issues having to do with the rotation of the Earth that show up in the hundredths place. So I generally like to just keep things at the tenths place. All right, now notice how I wrote the units. I wrote the units newtons per kilogram. And that's because it makes sense. I'm getting a force out, that's newtons. And the thing that dictates how hard gravity is going to interact with the object is the object's mass, kilograms. So this needs to be newtons over kilograms. Now, dimensionally, if you grind it through, and we'll see that that has the same dimension as meters per second squared, because a newton is a kilogram meter per second squared. The kilograms cancel. But, and this is super duper important, G is not an acceleration. Like I say, it is this quantity called the local gravitational field strength, which dictates how hard a planet is pulling on an object. In a future video, we'll be able to see how we can calculate this for any planet at any distance from those planets. But just to kind of give away a bit of the story here, by the time you are at the altitude where the International Space Station is orbiting the Earth, G is already 8.9 newtons per kilogram, and telecommunications satellites experience G at 0.223 newtons per kilogram as we get away from the center of the Earth. So it's not an acceleration. Now, a lot of texts, a lot of physicists will sloppily call this the acceleration due to gravity, but that is only true if you are in free fall. If you are in free fall, and only if you are in free fall, then we can draw the free body diagram and say that there's only one force, the force of gravity. Following Newton's second law of motion, this says that the acceleration is the net force over the mass, which is the gravitational force over the mass. And this mass is the inertial mass. So if we go and take the y component of this, when I put in the y component of acceleration, we know that the acceleration is going to be pointing down. We'll just say a sub y, and we know it's going to be pointing down, so we can put in a minus sign, and that's okay, because the force of gravity is pointing down, so minus Fg over this inertial mass. And then we can put in what our model of gravity says it's equal to. That's minus mg. But now here we need to be careful. This m is the gravitational mass. And this m here is the inertial mass. We cancel these not because they are the same physical quantity, or maybe they are, but experimental evidence says that they are, strongly implies that they are equal to each other. So in this particular case, we get that the acceleration is minus g, and sure enough, when you take newtons per kilogram, you can turn that into meters per second squared, and it's all good. But it doesn't have to be that way. For instance here, let's instead parachute our rock. So here's our rock, and let's say the parachute just opened. So in this case here, I don't know how fast the rock was going before, but it'll actually almost certainly be the case in this case here, if the parachute just opened, that the drag force is actually greater than the force of gravity. And we'll actually end up with a net force up and an acceleration up, because the whole point of a parachute is to slow you down. So again, we can do Newton's second law of motion here and say it's equal to F net over m, and this would be the vector sum of the drag force and gravity over m. So again, if we take the y component of this, it's going to be equal to d. The drag is pointing upward, so we say plus d. Gravity is pointing downward, so we say minus Fg over m. We can put in our model of gravity, and we can rearrange to get that this is d over m minus, we'll have mg over g as g. Whatever this works out to be, and it could literally be anything, it almost certainly is not equal to negative 9.8 meters per second squared. In fact, in this example, as I have it drawn, it's positive. It's not even a negative number. It's positive something. So this is why I make a big deal that g is not an acceleration. It just dictates how hard gravity happens to work. Now, because of this this experimental evidence that seems to imply that inertial and gravitational masses are equal, you very often, when working with gravity, will get a cancellation of the inertial mass against the gravitational mass, leaving just the gravitational field strength hanging out there as something that contributes to our final expression for the acceleration. But again, I can't reiterate enough, it's not an acceleration, it's a gravitational field strength. It just says how hard gravity works on something, how hard gravity pulls on something. And we have to take into account all the forces acting on an object in order to figure out its acceleration. Okay, I will also throw in a couple other issues. I have a little bit of beef to pick with the terms weight and weightlessness. So let's start with weight. There has been some good research done looking at textbooks in the English language, seeing how the word weight is defined. And while the researchers found that there's like 6 definitions, 4 of which are in some level of use, really there's just two really big ones. There's one that I'll call the apparent weight. This is what a scale reads when you stand on it. So this is actually a normal force. All right? Because if we draw a free body diagram, we'll have the gravity pulling down on you and the normal force from the scale pushing up on you. And what the scale is reading is usually how much a strain gauge sensor in the scale has been compressed. And that strain gauge is trying to return back to its original shape, pushing you up. This compression is proportional to the force of how hard you are pushing on the scale. And so it just is simply reading back how much the strain gauge has moved. This is maybe a little more obvious if you're standing on an old school spring scale as opposed to the more modern digital scales. There you can actually feel the whole scale move down a little bit as the spring compresses. But this is reading the normal force. Now, usually this is going to be equal to the force of gravity on you, but it doesn't have to be. For instance, let's say you got into an elevator with a scale and you pressed a floor to go up, and the elevator started accelerating up. So first it'll accelerate up, and then it'll get to a constant speed. Now when it accelerates up, in order for you to accelerate up with the elevator, the scale is going to have to push on you harder, up on you harder than gravity is pulling down on you so that you can accelerate up. But all the scale reads is what the strain gauge says, so it will say that you suddenly gained weight. But that's okay. When you get to your final floor, assuming you're going up, you have to decelerate to get back down to 0, which means that you will now be accelerating downward at faster than, you'll be accelerating downward, which means that the normal force of the scale will actually be less than the force of gravity on you. And again, the strain gauge just knows how much it's compressed. It knows it isn't pushing on you as hard right now, so it'll read a lower number, and then you're excited because suddenly you lost a bunch of weight until the elevator comes to a stop and we get back to reading your true weight again. So that's one definition that books use. The other definition used, again, in almost a perfect 50-50 split, is the gravitational force due to a planetary body on an object. So this is the force of gravity. And in the research that's been done, And this is just getting to the fact that physicists do not have a universally agreed upon definition of the term. Some books are very good about following their definitions, but a lot of them actually aren't. And so whenever you look at a problem that has the word weight crop up in it, really the first thing you need to do is figure out which of these two are we talking about. Are we talking about gravity, or are we talking about this apparent weight, basically the normal force, so that you can feel your sense of weight? Because you don't feel the earth pull down on you, you feel the floor push up on you, but you attribute that as your sense of weight, even though it's really a normal force. So you have to figure out which one it is and then solve for it. What this does mean is I recommend never using the symbol W in a free body diagram. Call it what it is. Call it gravity. Call it the normal force. That way you won't get confused when the problem is asking you to solve for the weight, because they might be asking you to solve for the other one. So just watch out for that. The other term related to that I don't really like is weightlessness. Turns out NASA doesn't like that term either. They call it microgravity, but I have problems with that term too. But I probably feel less bad about microgravity than I do weightlessness. So, how does a satellite orbit the Earth? Let's say we're talking the International Space Station here, and I really cannot draw this to scale. The International, at this scale, if I were to draw the International Space Station, there'd be only a tiny gap between the surface of the Earth and the space station. But I'm going to make it bigger so that we can more clearly see. So I'm trying to draw the habitation modules and the solar panels, and I'm sorry, it's just not going to be that good. Well, there's only one force acting on the object, and it is gravity. The Earth's gravity is trying to pull it into the center. Now, it's orbiting around. It just feels this one force of gravity in, and that means that it accelerates in to the center of the Earth. So when something is orbiting, it is falling to the center of the Earth. Now the issue is that it is moving sideways so fast, and it has to haul to do this too. It is moving sideways so fast that what winds up happening is you're just going around in a circle. That the force of gravity now becomes what we call a centripetal force. All the acceleration is what we call a centripetal acceleration. In other words, the acceleration is only responsible for changing the direction of the velocity, not the magnitude. We will more fully flesh out the ideas of centripetal force and centripetal acceleration in a future video. But for now, this is just like when we were looking at the car accelerating around a corner. It's the same deal, except the corner literally goes on forever. So the satellite is always falling to the center of the Earth, but it's going sideways so fast that basically the Earth keeps curving out from underneath it, and it never crashes into the surface. So why do we call this a weightless situation then when you're in the International Space Station? Well, let's say you're an astronaut in the International Space Station. You are falling at the same rate as the space station. So this means that you don't feel any normal force on you. There's no you don't need to have a floor pushing up on you or anything like that. You're just falling around at the same rate. And in fact, there is no well-defined floor in the space station. There are habitation, there's sleeping berths, and there's workstations and food stations and everything on literally, there are 4 surfaces, and literally all 4 surfaces have stuff on them. and they have to very carefully write labels on the walls so the astronauts know which way they're pointing. So because the walls aren't pushing on them, they don't feel any sensation of their own weight. In fact, this is actually a major issue and relates to two biomechanical things that are a deep issue of research on the International Space Station, because they have serious implication for the ability to do space flight to other planets. When humankind first started going into space, at first there was major concern. Would humans even survive the trip? So when they launched Alan Shepard, for instance, or Yuri Gagarin, first human in space, Alan Shepard, first American in space. When they launched Yuri Gagarin into space, they completely automated his capsule. And that's because they thought that he might be so disoriented, he might die. They literally didn't know what might happen to him. And so they completely automated how the capsule would operate. And he actually would have to punch in a special code number to prove that he was lucid enough if he felt the need to take over manual control. Alan Shepard was given more manual control because of some data from chimpanzees that were first flown into flight. But even so, he had to throw switches and stuff to be able to manually control things if he felt the need to. With time, we realized that surprisingly, humans are very resilient to this sensation of weightlessness. It turns out, though, that there are two issues. One is that if you are in space for prolonged periods of time, more than just, say, the few days the Apollo missions took to go to the moon and back, but if you're up there for a few months, you get some pretty serious bone density loss. And another issue is that you get permanent vision changes. And both of these seem to be due to the fact that the body is not feeling a sensation of its own weight. For the bone density loss, astronauts on the space station have to do a fairly vigorous workout regimen of a couple of hours or so, where they use all the huge collection of bungee cords, basically, to provide a gravity-like sensation so the body can still feel normal forces pushing on it to have a sensation of weight in order to try to reduce bone density loss. While not optimal, it seems to be doing okay, but it takes a huge chunk of time out and requires that astronauts be super fit because of how vigorous the exercise needs to be. The vision is an open research question. There are many promising things being done, but they are definitely both issues that we have to resolve before, say, we send people to Mars. I mean, at the very least, you need to figure out how to write new eyeglass prescriptions, because nobody's prescription will be the same by the time they make a trip from the Earth to Mars, for the most part. So anyway, NASA, recognizing that since it isn't weight in the sense of normal force, they didn't like that term. So they coined the term microgravity. But the thing is, you are still feeling a force of gravity, and it isn't micro. The gravitational field strength of the ISS is 8.9 newtons per kilogram, not 9.8. Okay, that's a reduction, but it's not even a 10% reduction. So, to call it micro, I find to be a bit of a stretch. But anyway, there you go. And catch you on the flip side.